Hello and welcome to LeChateliers Principle Part 1. In this video we're going to look at the effects of concentration and effective temperature on a system at equilibrium. There will be a separate video, a Part 2 video, that will focus on effects of pressure and volume. LeChateliers principle is a principle that predicts how a chemical system will react to a change. And this is a system that starts at equilibrium and then has some sort of a stress put upon it. Changes in conditions can be called stresses. The examples that we're going to talk about are going to be concentration and temperature, and also volume and pressure, which are pretty related, and also mainly we're dealing with systems with gases there. So we'll focus first on temperature and pressure, concentration and temperature. Equilibrium will do what we call shifting in order to counteract or relieve a stress. What it means to have an equilibrium shift. So when we're at equilibrium, remember, equilibrium is when concentrations are constant. And the reason these concentrations are constant is because rates are equal. So we have two opposing processes occurring, a forward and a reverse reaction. Because the rates of those two processes are equal, all concentrations in the system are remaining the same. So the first thing we're going to look at is we're going to look at an example of a school dance. So I like to kind of relate this to something for you. So if we imagine that here we have a school dance. And in this beautiful school dance, I'm sure you love my stick figures, we currently have 4 single girls hanging over here. So our concentration of girls is 4. We have 3 single boys hanging over here. And right now we have 1, 2, 3, 4, 5, 6 couples. So this system right now is at equilibrium. The girls in the corner are hanging out with their girls. They're fine. They're really happy together. They're having fun. The boys in the corner are doing the same thing. They're just hanging out. Couples on the dance floor are happy to be there, and everybody's happy. We are going to stress out this equilibrium. A school bus is going to pull up, beep, beep, and it's going to drop off a bunch of new girls. We got some girls in red here, maybe coming from another school or something. So if we start to add some girls to this scenario, so this girl comes over here, she's eyeing this dude, and she punches this girl in the face. It's kind of not that nice, but that's what happens. This girl runs over here like, I'm so sad. This girl over here comes in, she's like, yo, you know what, I like this guy right here. So she's like, hey dude, and then like she runs away. Now, one of these girls from over here, okay, so this girl right here might be like, oh, you know what, I found a shoulder to cry on right here, this guy. So now they're going to become a couple, and they're going to run off to the dance floor together, and we have a new couple forming. Another girl comes in. She's like, hey, I'm not going to start any trouble. I'm going to grab one of these guys over here that's already single. So these two are going to kind of come over here. Sorry, I'm having a little smartboard issue. And now they're on the dance floor. So what we did here is we changed the concentration of girls. So I added more girls to this. And when I did that, I now have 1, 2, 3, 4, 5 single girls. I only have 1 single boy left. We used those guys right up. And now on the dance floor, I have 1, 2, 3, 4, 5, 6, 7, 8 couples. So let's look at what happened here, okay? If we want to compare these concentrations, we started with 4 girls, 3 boys, 6 couples. We added more girls, so our concentration of girls is something that we messed with. So that number went up because we added it and because we have some more leftover girls there anyway. We depleted how many single boys we have, but we ended up with a higher concentration of couples. So by adding more girls, we stressed out this dance. That was a stressful situation, and things shifted. We produced more couples. We used up single boys. So there are 4 factors that can cause an equilibrium to shift, and remember, these are what we call stresses. So anytime you experience a change in your life, it tends to produce a little bit amount of stress. Same thing happens to a system at equilibrium. So a concentration change is one of these stresses, and that's kind of like the example with the girls at the dance. That's kind of like what happened there. So if we have a concentration change, so if I add to this reaction more of this, so I'm adding more H2CO3, What's going to happen when I add more of that is I have more of that to break down and form these two products. So since I have more CO3 breaking down, I'm going to have more CO2 being made, and I'm going to have more H2O being made. Now, the general rule we're going to follow here is a rule that I call add away, remove, towards. So what happened here was I added H2CO3, add away. So I shifted my equilibrium to the right, and I favored my forward reaction. So what I mean by all of this, by putting more H2CO3 reactant in, I favored that breaking down and making CO2 and H2O. The forward reaction had an increase in rate, while the reverse reaction really remained the same. So ultimately, I'll get more CO2 and more H2O. If I were to add CO2, by adding CO2, there is now more CO2 to react with H2O. So this is kind of like adding more girls to the dance. CO2 are like the girls, H2O are like the boys. So the CO2 is going to try to use up all that H2O. So when I add something, I shift away. So I'm going to add away. So I'm shifting to the left, and I'm favoring my reverse reaction. And when I shift to the left and I favor my reverse reaction, that's going to cause an increase in the concentration of H2CO3. Meanwhile, because I'm changing CO2, I don't have to talk about what's happening to the concentration of CO2. But because I'm taking that CO2 and reacting it to make H2CO3, I'm going to use up the H2O. So when I'm shifting towards the production of H2CO3, I get more of that. In order for this to make this, I'm using up that. So that's why my H2O is decreasing. Next thing I'm going to do is I'm going to remove something. So if I remove H2CO3, when I remove, I shift towards. So what this means is if I take this out of the reaction vessel, this is not available to do this and turn into these. So if I'm removing that from the reaction vessel, that does not stop CO2 and H2O from reacting and making more H2CO3. Some people like to think of it as, they're trying to replace what's being taken out. So when I remove something, I shift towards it. So since I'm shifting towards it, I'm shifting to the left. I'm speeding up that reaction and favoring my reverse reaction. What that's going to do is it's going to make me create, it's going to make me continue to create H2CO3 to replace the H2CO3. I don't need to talk about the concentration of H2CO3 since that's what I'm taking out. But as I'm shifting this way to make more of this, it's using up CO2 and H2O. So I'm going to have a decrease in CO2 and a decrease in H2O. So let's look now what would happen if we remove CO2. So when I remove CO2, if I were to take this out of the reaction vessel, what's going to happen here? H2CO3 can still break down and form these two things. But if I've taken this out of the equation, H2O can't react with it. So I can't form more H2CO3. It's just not there. It's not available. So those collisions can't occur. So when I remove CO2, I'm going to remove and shift towards. So I'm going to actually favor the production of the CO2, almost like to replace it in the system. So I'm shifting here to the right, and I'm favoring the forward reaction. And as I favor that forward reaction, I'm going to actually, because I'm taking this out of here, I actually cannot make more of this. So the concentration of H2CO3 is going to be decreasing. So we're going to have a decrease in H2CO3. However, I'm still making water, and if the water can't turn back into H2CO3, it just builds up in my container. So I'm going to have an increase in the concentration of H2O. So I did want to give you a little bit of a visual for this. In order to make this molecule right here, we need both of these. So when we take out CO2, that does not allow us to make this. However, this could still turn into this. So when we're talking about that forward reaction occurring, taking either CO2 or H2O out will prevent you from making H2CO3. However, if you take one of these out, you are still going to be having that decomposition happen. So whatever you have left there is just going to essentially build up in your reaction vessel. Temperature changes work similarly. We can still use the add, away, remove, towards. Only this time we have to make sure that we know where our heat term is. So in the reaction up here, we have a heat term right over here on our right side. So if we increase temperature, it is like adding heat. So by adding heat in this system, add away, what this means is we're going to push this equilibrium this way. Now the reason why is heat decomposes SO3. So if we put more and more heat in there, it's going to break that SO3 down in this decomposition reaction, which is the reverse reaction. So that's going to cause a shift to the left, and we're favoring our reverse reaction. By adding temperature, we're decomposing a lot of that SO3. So the amount of SO3 is going to decrease. Because we're favoring that decomposing into our products over here, the concentrations of SO2 and O2 are going to go up. We are favoring their production. Now, if we were to remove heat, so remove towards, if we were to take heat out of here, so if we decrease our temperature, what that does is makes less heat available to decompose the SO3. So since the SO3 can't decompose, we're not going to have as much of this going on. That kind of slows down. So we'll have less SO2 and O2. However, removing the heat doesn't prevent SO2 and O2 from reacting and making SO3. Some people like to think about this as you take the heat out, you shift towards the heat to replace it. So when we say remove towards, if we're decreasing temperature, we're removing heat. So we're going to shift this way. So we're shifting to the right. We're going to favor our forward reaction. And in favoring our forward reaction, we're going to have an increase in the amount of SO3. So the SO3 can still be produced, and since there's less heat, it's going to be decomposed less frequently, so therefore we'll have a buildup of SO3 in the container. Since we're favoring the production of SO3, but SO3 doesn't have the heat it needs to decompose back into SO2 and O2, our amounts of SO2 and O2 are both going to decrease.